Evaluate the definite integral from 1 to 4 of 4x squared e to the x cubed plus 1. Okay? Now, when I look at this, pretty elaborate expression. Okay? It's not something that I just, off the top of my head, know the antiderivative of, which is a shame, because in order to evaluate this definite integral, I need an antiderivative. So I need something, and then I'll plug in 4, and I'll plug in 1, and I'll take the difference. But the problem is, well, what is that something? Okay? So this is where, if we're confronted by something more complicated, we have to stop and break it down and use what we've learned. And in particular, I notice here, well, we've got e to a function. We've got a composition here. Now, that doesn't always mean that, hey, we're going to use substitution, but in this case, I really think a substitution is warranted. If you're planning ahead, right, if we're going to use substitution, this thing inside here is going to be my u, or my g of x. And so we also need to have sort of a g prime. We need its derivative around here. And yeah, roughly x squared, roughly, by the way, is the derivative of x cubed. Right? You lose a degree. So I feel more confident in doing a substitution. Okay? Maybe in the future, other questions, I'll need other techniques. But right now, yeah, I think substitution is warranted. So how does a substitution work? Okay? So we introduce our new variable, and it's going to cover all of the inside function, all of x cubed plus 1. Okay? And so then you take the derivative, so that'll be 3x squared, and you want to rearrange this to give you dx equals. So what we do, I'll do it down here, multiply both sides by dx, and then divide. And now I have dx in terms of du, and yeah, usually there's like a little function of x left around that needs to cancel out. But now I'm ready to do my substitution. Okay, so we'll have the 4x squared, but up inside the e, this x cubed plus 1, well, that's just what I've called u. And the dx here, well, that turns into du over 3x squared. Now, you're never, ever, ever done a substitution unless you get rid of your original variable. And fortunately here, the x squareds cancel out. If they didn't, and I had like a lingering x left over, I've done something wrong. Okay, maybe I made the wrong substitution, or I may have to try to rewrite that x in terms of u to get rid of it, because you can't have any of the original variable left over. And so if that were the case, right, just imagining, right, I'll get back to the question in a moment, but just imagining for a moment that there was somehow a leftover x, that this actually was x cubed, most of it canceled with the x squared, but we had a leftover x. What could I do? Well, I could say, look, I know u is x cubed plus 1, so u minus 1 is x cubed, so x would be the cube root of u minus 1, and then I could turn this into cube root of u minus 1, and then try and go from there. Because then, hey, I don't have any more x's, hooray, we did it. Okay? Now, of course, then you got to say, well, is this something I even know how to integrate, or should I use a different technique, or should I try substituting something else? But it's definitely something that can happen, that you can accidentally have leftover x's or whatever the original variable was, and you do want to be able to deal with them. Sometimes you deal with them by going back to the drawing board and saying, that didn't work. Other times you have to be creative and try and rewrite and rearrange functions, and remember that your substitution isn't just u is all of this. Sometimes the x can be something in terms of u. But, I've rewound too far. So the x squareds go away. Now we know that 4 over 3, that's a constant, that can come out. But we're getting a little ahead of ourselves. We're dealing with a definite integral. You got to watch out, these bounds will change. Okay? When you do a substitution, you have to plug the bounds into your function. So 1 along the x-axis turns into 1 cubed plus 1, turns into a 2 along the u-axis. 4 plugged in here, 4 cubed is 64 plus 1, we get a 65. So don't ever forget to change your bounds when you're doing a substitution with a definite integral. But there we go. Now, again, I've taken out the 4 thirds. And look at this, much simpler thing. I know the antiderivative of e to the u, it's e to the u. And so now we just need to plug in 65 and 2, and we're done. So 4 thirds e to the 65 minus e to the 2. That is it. That is the value of this particular definite integral.